My name is Duncan McElfresh, and I'm going to be talking today about matching algorithms for blood donation. This is some joint work we've done with Facebook. So I want to start out by motivating the problem. Safe blood is a scarce resource. So for example, every 2 seconds, somebody in the US needs blood. Developing countries especially have a high need, and this particularly affects children and women facing complications during childbirth. Not only is the need greatest in these countries, but supply also decreases with decreasing wealth. So for example, high-income countries have about 31 donations per 1,000 people on average. And as you move down the income spectrum, these donation rates drop off substantially. So there's been a lot of work studying the blood supply chain, which can be roughly divided into these 4 stages of recruiting donors, collection and processing, storage and inventory, and distribution and transfusion. In particular, there's been a lot of work in these last 3 stages from the operations research and optimization community. While the first stage, recruiting donors, has received less attention. Most of the work here has been on predicting demand spikes or predicting supply. So this is actually the area that we're going to focus on today, recruiting donors. So let me lay out this recruiting donors scenario a little bit more. So we have, we're going to assume we have a pool of potential blood donors, and we have several different donation opportunities. So we might think of this as donors and recipients in a given city. And in between these, we're going to have some kind of web application. And the way that these donors and recipients use the web app is the recipients, or the donors, will browse for different opportunities to donate, and they can opt in to receive notifications about these opportunities. Now, the recipients, these opportunities, they can state their need for blood, and they can also maybe reach out to donors or advertise themselves. Now, the role of the web app that we're going to consider today is to notify donors about opportunities using a notification policy. So it's this behavior, the notification policy, that we're going to focus on today. So from a high level, the research question we're trying to answer is how do we design a notification policy to increase the number of blood donations while also treating recipients equitably? And our contributions in this that I'm going to present today are, we first analyzed the Facebook blood donation tool, which is one of these online web apps. We analyzed this as a matching platform. Then we formalize a corresponding online matching problem for notifying donors. And then I'm going to show you some initial simulations and experiments that we've run to test this. So just a brief outline. I'm going to start by talking about our matching platform, so the Facebook blood donation tool. So the blood donation tool has been around for a few years. I think it launched last summer in the US. And as of this month, June 2020, it reports to have about 70 million registered donors. So there are 2 ways you can use the blood donation tool. One, if you're a donor, you can sign up, and as I described before, you can browse donation opportunities, and you can also opt in to receive notifications about those opportunities. You can also sign up as a blood recipient, and recipients are mainly hospitals and blood drives. At some point, individuals could sign up as recipients as well. And as I said before, these recipients will state their need, maybe a level of urgency or a blood type. So what I want to focus on today is the notification mechanism from donor that Facebook will send to donors. So as I said, many donors opt in to receive notifications about nearby recipients. And these notifications are determined by a notification policy. And this policy decides when to notify each donor and also which recipient to notify them about. So we might know that a certain donor has several different compatible recipients, and we'll decide when and which one to notify that donor about. So there are many questions I have to answer here, but the first question I want to address is, how do we determine the impact of a notification? How do we know that once we sent a notification, something good or bad happened? So we can't directly measure whether someone donates after we notify them, but we can measure actions that the donor takes within the web app. So for example, contacting the hospital or blood drive, the recipient, through the app, or making an appointment or a calendar reminder to donate, again, within the app. So I'm going to call these different actions a meaningful action towards donation. And this is actually the thing that we're going to be studying in our work. So we're going to use meaningful action as a proxy indicator for donation. And we're going to say that notification is successful if the donor takes action towards donating within, say, 7 days. So given this definition of meaningful action as a proxy for donation, we've looked through some of the initial data collected by the blood donation tool to ask who takes meaningful action and when, just to understand the type of problem we're facing. So some brief observations. Meaningful action is rare. Between 3 and 4% of all notifications sent lead to meaningful action. Donors who are more engaged with the Facebook app are more likely to take meaningful action. So for example, donors who use Facebook every day are about 40% more likely to take action than those who use Facebook less often. And also, if we notify donors about nearby opportunities, for example, less than 3 kilometers away, then they're also more likely to take action than if we notify them about further away opportunities. So these are just some very high-level observations in the data, and this suggests that there's some patterns in how these notifications and when they're sent will affect donors' behavior. And I want to emphasize that we have several other findings here that we report in our paper, and many of these align with previous literature on donor recruitment. So, for example, the distance measure here. So, a commonly reported result in the existing literature is that if donors perceive a barrier to donation, for example, a logistical or schedule conflict with that prevents them from donating, then they'll be less likely to take action towards donating. So that's exactly what we see here in the distance-based measure here. Okay, so I'm going to move away now from the donation tool and now talk about this as a matching problem. So we're going to think about this as a bipartite graph, where on one side we have our donors, you, and I'm going to say that these donors are offline, which means that they never depart the system, but we're going to be limited in how often we can notify them, how often we can match them. We're going to say that we can match them once every K days. And this kind of limit is natural for several reasons. One, we don't want to annoy donors. We don't want to have them experience notation fatigue. But also there's a natural limit on how often people can donate. So for example, based on where you live, there are different restrictions on how often you can donate whole blood. And that's somewhere between 8 and 12, 16 weeks. So it's natural to limit how often we bug people about donating. Now we also have recipients, and remember, recipients represent hospitals, blood drives, individuals. So some of them are always going to be available to receive notification or to receive donors, but some of them are going to appear and then disappear. So we're going to have some online vertices and some offline vertices on the V side. And so these can be parameterized, for example, by a probability that the vertex is available on a certain day. Now the edges that connect our donors and recipients, those are going to represent potential notifications that we can send. And we might add, for example, a cutoff between, we might only want to notify donors who are within 15 kilometers or 10 kilometers of a recipient. And these edges are going to be weighted, where those weights represent the likelihood that the donor will take action. So for example, on the previous slide, I showed you those different indicators of when people are likely to take meaningful action. So in our work, we've actually built we've trained a machine learning model to predict those things. And that will be the input then to our matching model here. Finally, we have some notion of time dependence. So donations are an ongoing process. And as I said, some recipients will appear and then disappear from the system. So we want to add we have a finite time horizon of, say, T days. Now, what is the solution that we have to this matching problem? I'm going to call this a matching policy, which is an algorithm that for every day in the time horizon and for each available donor, that is someone who hasn't been notified in the last K days, our matching policy either matches the donor to an available recipient or it chooses not to match the donor. So some examples of matching policies, we could have a greedy myopic policy that for every available donor, match using an edge that maximizes edge weight. We could also use a randomized policy, which is just match every available donor using any edge that's available. Okay, so this problem is related to standard online matching. Some of you might have noticed. So in standard online matching, you have U, the vertices that are completely offline, and V, vertices that are completely online. And in standard online matching, you have these online vertices V arrive one by one, and they have to be matched immediately and irrevocably to the offline vertices. And then both matched vertices are removed from the market. So you may have noticed that there are some similarities between our model and standard online matching. I'm going to go through those now. So in both settings, we have one side, U, which is completely offline. However, in both models, we have a fixed time horizon of T time steps. However, that's where the similarities end. So in our model, the offline vertices return after K days, while in standard online matching, the matched offline vertices are removed. Second, the online vertices, so the recipients in our case, in blood matching, they have unlimited capacity. So I could theoretically send as many notifications as I want about a particular recipient. However, in standard online matching, these online vertices typically have capacity 1. Finally, online vertices V arrive one by one in online matching. And in our setting, they arrive in batches. And again, some of these vertices are always present. So the batch size also changes. Finally, in standard online matching, typically it's assumed that there are far more online vertices than offline vertices, and the case in our setting is exactly the opposite. So we assume that we have, say, thousands or millions of donors and only tens or hundreds of recipients. So that's reflective of reality. Okay, so I've laid out some differences in the matching problem. Now I want to show you some brief initial results that we have. So the results that we can simulate, I'll show you 3 different policies we've simulated. So we can implement the greedy and myopic policy, the greedy and random policy pretty easily. And we also have a somewhat more clever LP-based policy. So this is based on the linear relaxation of the offline optimal matching policy. And if you want to learn more about that, you should read our paper. And so the LP-based policy basically randomly assigns, randomly matches donors in a more clever way than greedy or random. So the results I want to show you kind of go along 2 axes. So I'm going to show you these Pareto plots here for different cities. And on the vertical axis of these plots, I'm going to plot the total matched weight by each algorithm. So this is the total expected number of donations. And along the horizontal axis, I want to show the average weight assigned to each recipient, or the median weight assigned to each recipient. And this is going to be normalized by the expected weight that they would have received in a random policy. So this is going to be some kind of measure of fairness between recipients. So we want, on average, recipients to receive some fraction of weight that they could have received in a random policy. So the higher we are on the horizontal axis, the more to the right, that's the higher median overall recipients. And the higher we are on the vertical axis, the higher total number of donations we have. So as you might expect, when we use a greedy policy, we don't care about spreading donations between different donors. We only want to maximize weight. So often we maximize weight. So we're high. The X's here represent the greedy policy. And our randomized policy doesn't care about weight, but it randomly notifies donors about recipients. So we'd expect that the median recipient weight is higher here. So that's exactly what we see. And we can use different LP-based policies that kind of mediate between these two extremes of greedy and random. So I can show you some results from several different cities we've tested here. So a couple of observations from these simulation results are one, the increase that greedy achieves in the total expected weight over random is about 5 to 15%. Second, we see that by using the greedy policy, oftentimes this median recipient weight is close to 0. So this is the median normalized recipient weight. And what this means is that by using the greedy policy, sometimes very many of the recipients receive no notifications. And this is kind of an intuitive result. So let's say your city has 10 different recipients. Some of them might be very centrally located near the city center, say, and some of them might have a very well curated web presence or very strong advertising. Whereas some of them might be more rural, or they might have less of a web presence, so some will be more marginalized. And those will probably have lower edge weights or lower likelihood that donors will take action. So if we just blindly use this max weight policy trained by some machine learning algorithm, or guided by some machine learning algorithm, then we're going to prioritize some of those very high weight recipients over the low weight recipients. So that's why our median recipient weight will decrease if we use the greedy policy. So I want to very briefly talk about some fielded experiments we've run. So we ran some experiments on a subset of the Facebook donor population. This is using about 1.3 million donors, where donors are randomly assigned to either experience the random notification policy, which is kind of the baseline that's been used, or the greedy notification policy, where we provide some weight model. And these donors receive notifications once every 14 days. So there's no difference in the rate of notification. So for about, and we ran this experiment for 26 days. So what this means is that most donors only receive one notification. And our main finding from these experiments is that the greedy policy leads to a small but significant increase in meaningful action rate of about 5%. So I say significant in that it's statistically significant. And so this 5% is actually pretty similar to what we see over different cities in our numerical experiments. However, in these experiments, we can't study fairness because we don't compare different recipients. Okay, so I just want to wrap up. Today, I was telling you about a new opportunity where web apps and social media platforms can serve as a kind of coordination and recruitment tool for blood donors. We formalized a corresponding online matching problem, which is fairly distinct from standard online matching in several ways. So it offers some interesting theory questions. And finally, I presented some initial simulation and experiment results that indicate that even a slightly clever policy can result in about a 5 or 10% increase in donor action rate, which if you scale up to, say, a Facebook-sized donor pool, that's tens of thousands of additional donors taking action towards donation. So even a small increase can have a large impact in this setting. Great, and that's all I have for you today, so thank you.